I think it is no secret that I'm somewhat invested into telling machines what to do. For example, I have GLaDOS hanging from my ceiling and can tell her how to move, where to look, and so on. This is a good introduction into robotics, but being stuck on the ceiling isn't really helpful if I want to move more than mainly rotation. So, to make things very easy for me, of course I chose a geometry for a portable robot that is suboptimal and very complicated to start off with in robotic research, a hexapod. This video is actually a recap of the first version for a self-developed hexapod. This of course implies that there's already a second version in the pipeline. That one was actually shown as a short teaser a few videos back. The version of this video already does not exist anymore, and I gutted the parts from it and used them in the new version. The new version will also be covered in a video in the near future. This video will go through my thought process for how I decided on the geometry, how I designed and iterated the robot, how I wrote the programs to control it, what tests I did to conclude that this version was not successful, and finally, what needed to change in order for a better version. To kick things off, let me guide you through the requirements. To be able to replicate my developments in this video, you need the following areas of knowledge. First up, you need some basic understanding in mechanics. With this I mean you should be able to think about what parts you need to create a robot that can move in specified degrees of freedom. An example of this is covered in the next chapter. Second, some understanding of electronics and the skills to establish electrical connections are required. This sounds complicated, but boils down to knowing where to put the positive and negative leads of your power source, reading pin node diagrams, and crimping connectors or soldering connections. Next, you need to know how to program. While you don't need to be an expert at it, you might need some further knowledge than beginner level stuff. Of course, programming a robot requires some math. In this case, trigonometry is enough to get you through, but in the new version mentioned previously, this gets out of hand easily. You might also want to know how to define a coordinate system and how to calculate distances in 3D space. Lastly, you should have some material at hand to build something. This can be wood or metal that you can process by hand or machine. While the requirements might seem very generally defined, each one will have its example in the rest of the video. With the requirements covered, the design of concept will now follow. Now comes the fun part. How do I get from the idea of I want to build a robot to a physical object that is wired up and programmed? The first step is to clarify what kind of robot you want to build. I made the decision that I want to build a robot that can move freely in 3D space. The next decision is what kind of movement the robot should be capable of. As an example, let me show you my first inspiration to my own hexapod. This is a robot ant that I found online. It has 6 legs and a head. For movement, only the legs are required, and I will focus on these. The legs are assembled in 3 groups of 2 legs. The front and back legs are tilted away from the center legs. Each leg contains 3 servo motors. The first servo is on the hip of the ant, the second directly attached to it, and the last one is on the top of the leg. I will refer to these 3 servos as hip, knee, and foot servo in this order. For the total robot, 18 servo motors are required. This image was also the reason why I first gave this project the title Robot Ant, but I later changed it to Hexapod due to geometry changes. With the geometry somewhat defined, I then looked online for some inspiration. You can find several working hexapods on either YouTube or GitHub, and I took the freedom to use them as reference. The next step then is to design the complete body of the robot. Here you actually need to do several things in parallel to get a proper prototype, unlike mine. The size of the robot should be defined before designing the body. Here, a good guideline is the size of the motors for the individual joints. These also come with a torque rating, and this should be your main guideline. In my case, I used 9G servos because I did not want to spend as much on my first prototype, since I need 18 of those. Anyway, my design was then created without any of the considerations just mentioned. The whole model consists of 11 part types, where many need to be created several times. The overall dimensions of the first iteration were 54 cm length, 40 cm width, and 15 cm height. This might not seem that large, but you will see how large this actually is later in this video. I did a second iteration where I reduced the size of some parts, putting the dimensions to 40 cm length, 35 cm width, and 12 cm height. The overall design process was done in many iterations, so don't expect everything to work in the first try or the 10th try. To properly design the required parts, I modeled up the electrical components that I will use in the robot, like the microcontroller or the servos. This made it easier to check in the model if the parts would actually fit together with the rest. Speaking of electronics, I somehow needed to control 18 servo motors with a microcontroller. Luckily there are PWM boards available that enable me to do exactly that. For this version I used 2 of the PCA 9685 I2C boards. Each can handle up to 16 motors by themselves, but since I had 2 more I decided to split all motors onto 2 of the PWM boards. For the microcontroller, I chose an ESP8266 Node MCU version 3 board. This was mainly done because I need a lot of memory and compute power to control all servos. As for powering all electronics, I simply hooked up the robot to my lab bench power supply. This is not good if you want a robot that can move freely, since you are bound to the power supply. But since these are my first tests, it should be fine, and this issue got solved anyway in the newer version. The last part is how to program the robot. I first wrote some programs for testing the PWM boards and then to calibrate all servos. This is to ensure that the servos rotate in the same direction and is required for the programs that will follow next. In robotics, it is common to solve the inverse kinematics of your joints. This enables you to give the robot coordinates in a Cartesian coordinate system instead of providing each joint angle. The inverse kinematics determine the joint angle from the given coordinates. There are several ways you can solve the inverse kinematics of a robot. In my case, I used basic trigonometry. Here, you can work your way through the different axes of your coordinate system. For example, I needed to modify and pass on one of the lengths in the leg to the next stages to get the formula for all joint angles. I will skip further details on the math to save time, but if you want to have a look at it, feel free to pause the video or check out the files uploaded to my GitHub. The link is in the description. Implementing the inverse kinematics in code enables me to test in the real world if the math is correct. Here, I simply passed the values from the inverse kinematics to all legs. The last programs implemented a sequence of coordinates to get the robot to stand up. This test is my main test to see if the current robot is actually capable of walking. If it cannot support its own weight, I don't need to bother trying to get it to walk. One last thing, when using servo motors in this fashion of giving target coordinates, the movement should not be with maximum velocity and acceleration. This results in a way higher power draw and unwanted movements and oscillations in the joints. To combat this, I prepared a simple model for each servo according to a PT1 module. This means that the model reacts somewhat fast at the beginning and then slowly approaches the target. This is shown here as an example. The curve might remind you of the voltage curve a capacitor produces. This model will be implemented during the tests for each individual servo. This is the general overview over all things that I needed to come up with in order to go from an idea to specific requirements and designs. The next step is now to build everything together in order to test it. To start off, I first needed to build the robot. For this, I printed out all parts on my 3D printer. Since I needed to iterate pretty much all parts, I therefore printed a lot of parts, many of which landed in the trash. I started printing the parts for the legs, specifically the middle sections that will hold 2 servo motors. When I got the dimensions and tolerances right, I continued with the feet. These are kind of arcs that bend downwards. To move the individual joints, I printed these grooves in place to hold the small plates from the servo motors. This way I ensured that the joints actually rotate and that the parts are properly attached to each other. The next part to print was the hip. This is the connection between the leg and the main body. As you can see, because I always need to do this part 6 times for all legs, it quickly got messy with all the cables. When everything was wired up correctly, it already looked much more like a robot than a mess of cables and parts. Adding the joint parts of the main body connected each leg group together. Together with the sections between these joint parts, the robot was nearly finished. The last small part is the tray for the microcontroller. Wiring everything up was easy since the body is mainly hollow. The 2 PWM boards are mounted in the long sections of the body, the microcontroller at the end of the robot. The robot gets its power via the 2 small cables hanging out of the side on the long section of the body on the front. Here you can see the first iteration of this version in its full glory. As said previously, it is very large. This also means that it has a significant weight of 617 grams. To get a bit ahead of myself, here is also the comparison to the second iteration of this version. You can see the direct comparison in size of the 2 bodies here. After the first tests, I gutted the electronics from the first iterations and put them into the second iteration. The overall wiring and geometry did not change, I just removed unused areas to make the robot more compact. Unfortunately, I forgot to weigh the robot, but it was significantly more light than the first iteration. With the robot now on standby, let's do some tests with it. Since I tested a lot of things, this chapter will be a bit longer than usual. The first thing that I tested was the behavior of each individual servo. This gave me the information needed for the calibration, where I redefined the 0 value and the movement direction. A small section of the program is to convert a given angle into the actual angle of the servo based on its calibration. With the calibration done, the next thing was to let the robot stand up. Here I directly noticed that the legs had trouble lifting the weight of the robot. Neither of the 2 iterations of this version were able to lift themselves up. Still, the servo torque and friction were enough to keep it standing when I lifted it manually. Here you can really see how large the first iteration is. It takes up nearly my whole table. I then went on to test if the robot can stand on 4 of the 6 legs, and indeed it can. The second iteration behaved very similar to the first iteration. Although it cannot lift itself up, it can hold its position. The third test is to test out the servo model for motion smoothing. This video here shows a homing sequence which is without the servo model, and then afterwards some movements with the servo model. Here you can directly see the difference between the two. The homing sequence is very discrete in its steps, and the whole robot shakes due to the movements. The smooth motion is much more stable, but also takes longer to complete. The fourth test is to test the inverse kinematics model. Here you can see a short clip of moving the foot along one axis. While the motion is not perfect, it is still visible that the foot travels along a line instead of an arc. This is achieved by using multiple joints instead of just one. A later test combined the inverse kinematic model for all three axes. Here you can see that the feet clearly travel in a Cartesian way instead of along arcs. I also did an additional test for powering the robot with a battery mounted on itself. Here I needed to mount the battery itself and add some electronics to step down the voltage to a usable voltage for the rest of the electronics. This clip here shows that the Hexapod is able to power itself and to move. Tests showed that the supplied power was still insufficient and it was not able to stand up by itself. That was it for the tests. Let me collect my findings that I gathered with this version. Overall, I can say that this robot was somewhat successful. While it cannot stand up by itself, it definitely could stand by itself once I lifted it into place. The realization showed that I figured out how to build a robot that can actually move. The built robot also shows that I did not put too much thought in the overall geometry and the dimensions. The robot is very large and way too heavy for the small 9G servos, especially with the large levers in the legs that cause large torques. The tests show that I am capable to implement things like motion smoothing and a first try at inverse kinematics. This will pave the way for the second version of the robot. I also managed to power the robot by itself, meaning for the second version I will not be bound to an external power supply. One thing to keep in mind is also the cost of building such a robot. I spent a total of roughly 86 euros on the robot, as it was shown in this video. The main cost will come from the motors, so I recommend that you should start your own robotics project with a more simple geometry, as it also will be a bit cheaper. While the result might be a bit disappointing with a robot that cannot walk around, I learned a lot during this research. This is the great thing about engineering and prototyping. Failure often teaches you a lot more than success, and exactly this was already demonstrated in the teaser a few videos back. This brings me to the outlook. For this project I have planned great things. The next version of the Hexapod will be completely redesigned. This is done on the basis of taking resulting torques in the joints into account and to minimize overall size and weight. The body will be centered around the largest part, which will be the battery. This new version will then be calibrated and tested extensively. One test is of course to see if it can stand up, but I want to go further than just some simple movement tests. I want to fully implement an inverse kinematic model in all 6 degrees of freedom, at least for standing. Since controlling the robot was done via USB and a computer, I also want to be able to remote control the whole thing. From here on out, I might iterate the design again and again. Overall, the end goal for now is to have a robot that can move according to inverse kinematics. This also includes taking steps and moving generally freely in 3D space. The robot should also be remote controllable. These two goals are enough for now, but I probably will do some complex stuff when these goals are achieved. This project actually took place quite some time ago, but I wanted to document it in a video anyway. Right now, handling the last words is boring, and to also give you a teaser for my next video, Auto will take over the rest from me.
Greetings. The overall development shown in this video took place during October of 2021, and development of the next version is in process since February of 2022. The first prototype was evaluated and errors were identified. These are considered during the next prototype. The expected improvements will lead to improved robot performance. The next video will provide you with the information about how I gained the ability to communicate like demonstrated right now. Until then, goodbye and thank you for watching.